I'm Srani Anantapantala, and this presentation is going to be about the structural properties of a Cartesian product with itself n times, or K and M. So what is K and M? Well, K and M is equivalent to an m-Ary n-dimensional hypercube, where m is greater than or equal to 2, and n is greater than or equal to 1. A hypercube, which is denoted as HCMN, has m to the power of n vertices, and each vertex is represented by an n-digit number from which is represented by A0, A1, all the way to An-1, where each element is a number from 0 to m-1. We call each digit in the vertex an element. So each digit, AI, is a number in the positive number in the range 0 to m-1. Now, two vertices are only adjacent when one element in the two vertices is different, and all the other elements are the same. So this is an example of a hypercube. We can see that this is HC23. So as you can see, if two vertices are adjacent, only if there is one element in the vertex, or basically one digit in the number denoting the vertex, that is different. Also, we can see that there are two subcubes, H of 0, which is in green, and H of 1, which is in red. H of 0's vertices to the subcube each have the last element or last digit as 0, while in H1 subcube, the last digit or element is all 1. So HCMN can be partitioned into m disjoint subcubes or subgraphs, and those are called subcubes. Each subcube contains a set of vertices where the nth element or the last digit is the same, just like we saw in the example on the last slide. For example, in H of I, each vertex has I as our last element. Now, each subcube is isomorphic to HCMN-1. So because we're looking at the connectivity properties of a hypercube, let's say that F denotes the set of vertices deleted from the graph, while F of I is a set of vertices deleted in specifically the H of I subcube. So we also know that a hypercube has a vertex connectivity of n times m-1, meaning if we delete less than n times m-1 vertices, the graph will still stay connected. So HCMN is n m-1 regular. So there are a couple of properties of hypercubes that are very important for these proofs. And that's what they were. So our goals are that we're examining the fault resistance of m-Ary n-dimensional hypercubes when a small number of vertices is deleted, specifically about 2 or 3 times the regularity of the graph. Our main result is a bound in terms of m or n on the greatest number of vertices that can be deleted from the hypercube, such that the graph is still connected or has a large connected component, which we can call C, and some number of small components with at most 1 or 2 vertices in total. So in theorem 2.1, we're trying to prove that if at most twice the regularity is deleted, so specifically, if we delete at most 2 times n times m-1 minus m-1, then the resulting graph is either connected or has at most one singleton. So first, let's note that our base case, when m equals 2, HC2n is an n-dimensional hypercube, which means that deleting up to 2n minus 3 vertices leaves either a connected graph or at most a singleton, which is our claim. So let's assume that nm is at least 3. And we'll proceed with induction on n. You might be wondering, why was this bound used? And why was the bound tight? Well, this number was derived from the common neighborhood of 2 vertices. So first of all, each vertex is adjacent to n times m-1 minus 1 total other vertices. and two adjacent vertices, say U and V, have m minus 2 common neighbors. So the common neighborhood of these two vertices is 2 times n times m minus 1 minus n. Hence, it's possible to delete those many vertices and have at least 2 vertices that are separate from C. So in order to have a resulting graph with at most one singleton, 2n times m minus 1 minus m minus 1 was the best possible bound. So under our base case, when n equals 1, the graph HCM1 is complete on m vertices. Thus, when we delete up to m minus 3 vertices, the resulting graph is, of course, still complete, and that means it's connected. For n equals 2, we delete up to 3m minus 5 vertices. Firstly, each subcube HCM2 is isomorphic to the complete graph on m vertices, which means we only need to show that there is at least one edge between any two pairs of cubes. So we can show that. So let's say that the cardinality of f of 0 is less than the cardinality of f of I, where I is greater than 0. Then the cardinality of f of 0 is less than 3, and we only have 3 cases where f of 0 has a size of 0, then 1, then 2. When there are no vertices in f of 0, the resulting graph is connected. Now, when there's one vertex in f of 0, there is at most 2m minus 1 more deleted vertices, which means that at least one more vertex is isolated from the rest of the graph, since each vertex has m minus 1 neighbors in the other subcubes. Lastly, when there are 2 vertices in f of 0, at most m minus 5 vertices are deleted from the rest of the graph, and that means there's still an edge between a pair of subcubes, and they all belong to a large connected component, which we will call C, and thus this lemma has been proved. So we can assume that our statement holds when n is at least 2. Okay, so we just showed the base case. Here's like an outline of our proof. We'll next be showing that when deleting 2 times n plus 1 times m minus 1 minus m minus 1 vertices, the resulting graph is connected or has at most one singleton separated from C. To do this, we'll use casework on the size of f of 0, which let's say is the largest vertex set of vertices deleted in any given subcube. So in case 1, since the size of f of 0 is less than or equal to n times m minus 1 minus 1, and the vertex connectivity is n times m minus 1 of a regular HCMN graph, the subcubes themselves are connected. A pair of subcubes that has at least one edge between them, because the maximum number of subcubes, the maximum number of vertices we delete in these two subcubes is less than the number of edges between the subcubes, so the resulting graph is connected. Then in case 2, where the cardinality of f of 0 is at least n times m minus 1, and at most 2n times m minus 1 minus m minus 1, there is at most one more subcube equation that is true. So let's call the set of vertices f of 1. The rest of the subcubes follow case 1 and belong to C. So if we use induction hypothesis, h of 0 minus f of 0 and h of 1 minus f of 1 each have at either a connected graph or at most one singleton separated from C. The large components of these subgraphs are part of C because we delete less vertices than the amount of independent edges between two subcubes. Thus, in the induction hypothesis implies that there are at most 2 singletons, which isn't possible because that would mean we deleted at least 2 times n plus 1 times m minus 1 minus m vertices, which contradicts the assumption of size f. Thus, there is at most one singleton that concludes there is at most one singleton, and that concludes case 2. Then for case 3, the size of f of 0 is at least 2 times n times m minus 1 minus m. Then the rest of the subcubes are, by using case 1, a part of C. Each vertex in H0 minus F0 has m minus 1 outside neighbors, and because we delete less than 2 times m minus 1 vertices from C, at most one singleton is separate from C, and that case is true, concluding the proof. So in theorem 2.2, what happens if we delete even more vertices, say 3 times the regularity of the subcube? So this is what theorem 2.2 is about. If we delete at most 2n times m minus 1 minus 2m minus 1 vertices, we want HCMN minus this f to be either connected or have C and at most 2 vertices separated from the graph in total. So again, let's assume m is greater than or equal to 3, and let's proceed with induction. So of course, the bound is the basis of this theorem, but again, why is that bound tight? Well, we picked a bound of this 3n times m minus 1 minus 2m minus 1, again, because of the common neighborhood of this time 3 adjacent vertices. These 3 vertices have m minus 3 common neighbors. So to possibly isolate the 3 vertices, 3n times m minus 1 minus 2m vertices could be deleted. So to isolate at most 2 vertices, the bound 3n times m minus 1 minus 2m minus 1 was the best fit. So as said with the first theorem, when n equals 1 and n equals 2, our statement is true. For this proof, we need to also make sure that when n equals 3 is also true. So when n equals 3, we delete at most 7m minus 10 vertices. Then each subcube has at most 2 vertices separated from it, according to the lemma when n equals 1. Then 3 times m minus 1 more vertices are deleted. Isolating more than 2 vertices from the graph is not possible, so it will require more than 7m minus 10 vertices to be deleted. And also, the large components of each subcubes are connected because we know that there is at most one edge between them. Thus, we can say at most 2 vertices are separated from the large connected component. So in this theorem, we can assume that n is greater than or equal to 3. Again, we'll assume that the cardinality of f of 0 is greater than the number of vertices deleted in any other subcube. So here we again we're trying to show that by deleting 3 times n plus 1 times m minus 1 minus 2m minus 1 vertices, the resulting graph will have at most 2 vertices separated from C, as we're going by proof by induction. So case 1 is the same as case 1 from the first theorem. The result in the entire resulting graph is C. Now for case 2, we're using the induction hypothesis from the previous theorem, except here there are 3 subcubes where the number of vertices deleted is greater than n times m minus 1 minus 1. From the last theorem, we saw that there is at most 1 singleton in each subcube. However, 3 singletons is not feasible, as that would exceed our bound. Hence, at most 2 vertices can be separated from the graph with this bound, and this uses similar reasoning from our previous theorem, and the connected components would be part of C. So case 3 is really similar to case 2. There is only one subcube that is greater than or equal to having 2n times m minus 1 minus m vertices deleted. We can actually say from the induction hypothesis that h of 0 minus f of 0 has at most 2 vertices separated from C. Firstly, similarly to the first theorem, the connected components are connected to each other to make C. So like case 2, to have even more than 2 vertices separated isn't possible because that exceeds our bound. This proves case 3. Lastly, in case 4, we're trying to say f of 0 is greater than or equal to 3n times m minus 1 minus 2m. Then at most 3m minus 4 other vertices will be deleted from the rest. And according to case 1, hi minus fi belongs to C. we can say that the large component of H0 minus F0 is part of C for similar reasoning to case 2, because it's less than 3 times m minus 1 vertices deleted outside. So at most 2 vertices remain separated from C. And with that, we can conclude this case and the theorem and the proof for the theorem 2.2. So to conclude, we gave the bound of the number of vertices that could be deleted from an m-Ary n-dimensional hypercube to guarantee that the graph is either connected or has a large connected component with up to 1 or 2 vertices separated in total. So our further results will be working on creating a more generalized bound in terms of n, m, and r that results in either a connected group or small components of at most r vertices separated from C. And with that, thanks for listening, and I'd be happy to take any questions at this point.